everybody. My name is Gautam Kunapuli, and I'm the author of Ensemble Methods for Machine Learning. And today I would like to talk about gradient boosting from scratch, which is chapter 5 in this book, which is currently in MEEP. Here are some links if you want access to these slides. They're on my GitHub page. The link to the book as well as the companion Jupyter notebooks. So gradient boosting, it's all over the place these days and is widely considered the state of the art in machine learning. If you've ever taken part in a Kaggle competition or are generally interested in seeing what all the Kagglers are doing these days, and also if you've been reading a lot of machine learning blogs and things like that, you'd have probably seen the term gradient boosting pop up a lot. And it's being used for a wide variety of data science problems and challenges. And so it is rightly considered one of the state-of-the-art machine learning algorithms. So we're going to kick off here by motivating, the need for gradient boosting and why we need to understand it by posing this highly bothersome yet utterly unavoidable question. Which machine learning algorithm should I use for this data set that I have, right? And this is, of course, an age-old problem. Everybody wants to know the answer to this question. And, over the last few years, last couple of decades even, there have been extensive studies by various authors in academic circles, at least, to try and figure out what the answer to this is, right? And so this first work in 2014, for instance, analyzed about 17 families of machine learning algorithms on 179 data sets, right, which are publicly available. And they concluded, based on the algorithms and models that were available at that time, that random forests were the best, and their performance was comparable to support vector machines. And this kind of represents, our understanding of the state of the art at that time, right? So the 90s and early 2000s were all about support vector machines, and then we transitioned to random forests, which are also an ensemble learning method. And now, more recently in 2018, a study was performed, and in this case, they also threw in gradient boosting classifiers, right? And what they came up with was that out of the 165 data sets, compared them pairwise, and here are the algorithms and the families of algorithms that they compared, right? So we have gradient tree boosting, random forests, extra random forests. These are all Ada boost is in here. These are all examples of ensemble methods. But also, some classical machine learning algorithms such as, stochastic gradient descent, k-nearest neighbors, decision trees, logistic regression, and so on and so forth. And, the leftmost column is basically the percentage of data sets that these algorithms were able to beat gradient boosting on. So for instance, random forest was only able to beat gradient boosting 9% of the time on these 165 data sets, right? So if you were to go ahead and rank all of these algorithms, you'll see that gradient boosting, and these are all results from this paper by Olson et al., right? That gradient boosting is in fact the most successful on a wide variety of data sets that they considered in their study. And up there are several other ensemble methods such as random forests and extra trees and Ada boost somewhat fallen behind. And so this kind of gives us, a way to answer this highly bothersome yet utterly unavoidable question: which machine learning algorithm should I use for my data set? And all of this, seems to suggest that gradient boosting is where we want to go. And this kind of sets up our motivation for looking at gradient boosting today, right? And so gradient boosting is a sequential ensemble method. In short, it's an ensemble method, which is essentially a collection of machine learning algorithms, right? So you put together, instead of training one giant model, you train several models, and then you put them all together and you aggregate their predictions, and that essentially gives you a machine learning ensemble. And commonly, there are two types of machine learning ensembles. One of them is known as parallel ensembles, where several models are trained in parallel, and their predictions are aggregated together to give a final prediction. And in typical cases of parallel ensembles, the base models, which make up the ensemble, are typically strong learners. And a strong learner is one where you would expect, good performance, high performance, basically as a rule of thumb, right? Sequential ensembles, on the other hand, operate sequentially, as the name suggests. So what they do is they take the data that you have and build a first model, and then they try to identify where that model is failing. Essentially, so in terms of a classification problem, it would mean you'd want to try and figure out where the first model that you trained, M1 over here, is failing, and then you try to train a second model, M2, such that the predictions, on those misclassified examples are improved upon, and then you see how well the ensemble of M1 and M2 is doing, and then you try and identify now what the misclassifications are, and you train a third model to add into your ensemble, and so on sequentially, one after the other, right? So this is in direct contrast to the parallel ensembles where all of these models are kind of trained together in parallel, whereas in sequential ensembles, you have to train them one by one because the one you're training currently will have to fix the mistakes of all the models that you've trained so far, the ensemble that you have until now, right? So gradient boosting is an example of a sequential ensemble algorithm. Parallel ensembles, I'm sure you're familiar with. They include methods such as bagging and random forests, whereas sequential ensembles include methods such as AdaBoost, which is adaptive boosting, and what we're going to look at today, which is gradient boosting, right? So the key for sequential ensembles that we want to keep in mind is that every time they train a model, they do so to basically fix the mistakes that have been made by the previous model. And the other thing you want to keep in mind when it comes to these kinds of sequential ensembles, such as gradient boosting and AdaBoost, is that the base estimators, these models that you're training in every iteration, are typically weak learners. So a weak learner, in contrast to a strong learner, is basically a machine learning model that is not overly complex, that achieves, you know, reasonable performance. In absolute, in strict terms, a, a, a weak learner for classification has to do barely better than random guessing, right? And so it turns out that you can put together a whole lot of such weak learners to boost their performance into a strong learner. So that is basically what sequential ensemble methods do, and that is exactly what gradient boosting does as well. Uh, and so since we're talking about gradient boosting, it is also, ideal to delve into this and try and figure out how they achieve this key thing, which is to identify the mistakes that have been made by the current model, right? And to do so, it's also kind of useful to characterize what gradient boosting does and then contrast it with what other boosting algorithms such as AdaBoost do, right? So for these sequential boosting algorithms, the key is to identify where the mistakes are and get the base learning algorithm to focus on these misclassified examples. So in the case of AdaBoost, the figure on the left, you can see that this is a binary classification problem over here and a simple illustration, and you can see that there are two misclassified examples. There are these squares and the circles, but there is one of each that is misclassified and on the wrong side of the classifier. In order to get the base learning algorithm to focus on these in the next iteration, AdaBoost uses weights. So it has a clever way of computing weights, and so the more confident it is that it has done the correct classification, the lower the weight will be. basically saying that I think I have classified these data points correctly, and so they will have lower weights. On the other hand, if they're misclassified, then those corresponding points will have higher weights, which here are these 2 points, the circle over here and the square over here, which are misclassified, and so they would have higher weights. And in this way, you give these training examples along with their weights to a base learning algorithm, and you can use that to train a weak classifier. On the other hand, gradient boosting also needs a way to, characterize the misclassifications of basically characterize the mistakes made by the algorithm, figure out what's going on, and in a similar way to AdaBoost, get it to focus on those specific data points. But instead of using weights, it uses something called residuals. A residual is just an error, right? So in this case, again, with these 2 training examples, if AdaBoost gives them high weights, gradient boosting will essentially compute residuals, and the sign of the residual, as well as its magnitude, basically give us an idea of which way we should push our new model to adjust its behavior so that it does correct classification. So this is kind of the intuitive basis for the difference between AdaBoost and gradient boosting, right? And this is essentially going to be the core focus of what we're going to be looking at over the next 30 minutes or so, which is essentially how can we measure these residuals for these training examples, which ones essentially do we focus on when we build our models, how all this works in practice, what do the trained models look like, and so on and so forth. The other thing that gradient boosting does is it approximates gradient descent. Now, gradient descent is an example of an optimization algorithm. Basically, anytime you have a loss function in any machine learning problem, you ultimately want to optimize your loss function. And many machine learning algorithms use several different types of optimization algorithms, one of which is gradient descent. If you're familiar with neural networks, there's a variation of gradient descent that neural networks use called stochastic gradient descent, and there's a whole lot of variations on that front, and so on and so forth, right? But broadly, you can think of gradient boosting in general, but specifically gradient boosting as a means of approximating gradient descent. So in this case, for instance, in the example on the left, you have this loss function that you want to optimize. It's a squared loss, right? So a loss function essentially is going to tell you how badly you're doing or how well you're doing, right? So here, the squared loss is going to measure the difference between the true label, which is y, and your predicted label, which is f0 for this particular model, and then it's going to square the difference. So if the difference between the true and predicted is pretty big, the square is going to be bigger still, and the loss is going to be a large number. On the other hand, if y, your true label is close to your predicted label, then what's going to happen is that their difference is going to be small, which means that the the squared loss is also going to be correspondingly small. So this is a way for, a loss function is basically a way for us to characterize for each training example, and indeed over the entire data set, how well the model that we have at the moment is behaving, right? How is it performing? And you can obviously, measure your loss on the training set. And the goal, of course, is to keep updating your model until you achieve small loss, right? That is what training is in the overall grand scheme of things. And so when you use an approach like gradient descent, an optimization method like gradient descent to do training, then it's going to also essentially iteratively compute a sequence of steps. And it's going to basically move from your current solution to the next solution, and then update it again to the next iterate, and then update it again to the next iterate until we converge, right? So at the bottom here, you can see this is just an example function, right? What happens with gradient descent, right? This could be an example of a loss function, very similar to the squared loss. It's got 2 minima over here, And so how does gradient descent work? You begin with some initial guess, and then you compute the gradient. The gradient basically is the slope at that point, right? But interestingly enough, the negative gradient is going to tell you which direction you should be going in so as to get the biggest decrease in your loss function. So in this case, the negative gradient, if it's going to look in this direction, you move in that direction, and then you get to your next iterate, which is your function f1, and then you're going to compute the gradient there, move in the opposite direction to the gradient, and continue to descend. That's going to get you to f2, and then you're going to carry on to the next iterate, to f3, so on and so forth until you converge. This is how gradient descent works. It's a classical optimization algorithm. On the other hand, gradient boosting is going to work in pretty much a similar way, right? But instead of explicitly computing the gradients at each iteration, we're going to learn to approximate the gradient at each iteration. So what this lets us do is you can see that, here, if you replace the true gradient with this thing that we've learned, the final model that we have, F3, is really going to be, if you backtrack from here, right? F3 is going to be, this, this H3, which is your approximation here, plus H2, which is your approximation here, plus H1, which is your approximation here. So sequentially, what you will do is you'll start with your initial guess. You will then build a weak learner here to perform, this approximate gradient descent, and then you will end up at a model which is essentially F0 plus this weak model. And now from here, you compute the gradient again, and then you learn a weak learner, a weak estimator. And now your new model is going to be F0 plus H1 plus H2, right? So you've sequentially added a weak learner to it. And now you're going to repeat it. And when you get to F3, your F3 is going to be F0 plus this weak learner, plus this weak learner, plus this weak learner. So F0 plus H1 plus H2 plus H3 until you get to, and then you keep carrying on with this procedure until you basically terminate in this case. And you have and there are some criteria for termination that we can talk about later. So this is essentially the analogy between gradient descent, which is commonly used in optimization, over loss functions, and here gradient boosting, which is basically a procedure that also tries to capture this kind of behavior, right? And so putting all of these things together, gradient boosting can be viewed as gradient descent, which is an optimization algorithm, and boosting, which is an ensemble method. So if you, and that is precisely what gradient boosting does, right? So remember, to recap, what boosting wants to do is it wants to sequentially learn, these weak models, one model at a time, in such a way that we are fixing the mistakes made by the previous model. And what gradient descent does is it sequentially updates your, your progress over this loss function profile. And so you can see now through these two that your gradient descent and boosting combined together essentially gives you a gradient boosting procedure. So the key then is that we are going to be, instead of explicitly computing these gradients, we are going to be training weak learners, because that is what boosting does, to essentially capture and the mistakes that the current estimate makes, and then go ahead and fix them by using the residuals as a means of understanding how far off we are and how much we need to adjust our current model.